I want to introduce Professor Galan Moody. Galan's an associate professor here. Came to us from the National Institute of Standards in Boulder, where he, between there and CU Colorado, he did his PhD at an institute that's jointly managed by those two entities. Yeah. Galan's won a number of early career awards. He's been around. How long have you been here now? 5 years?
Not quite. Four and a half. Yeah.
4 years. Okay.
Yep.
And let's see, he runs the quantum photonics lab here, and his lab is on the first floor. Steve's lab is also on the first floor, so during the lab tours. He also mentioned Phil Christopher's lab, which he's working with. He's up on the third floor. So we encourage you, those labs will be available and open in the lab wing here, which is right past that screen there at 5:30. One more logistical item. We're going to extend this to 4:45, these sessions and all that. We'll finish up at 4:45, and that's when we'll start the reception. So you won't miss any wine or anything if you stay in here and all that. Let's see. What else? Oh, and he's one of the leaders of the Institute's efforts in quantum. So, all right, with that, Galan, thank you very much.
Yeah, thank you so much. It's a pleasure to be here. Thank you, and thank John and others for the opportunity to present some of the research going on campus in sort of the quantum space. I think it's not really emphasized very much in terms of quantum technology and efficiency, but they really do go hand in hand. And one of the main reasons for that is that the quantum signals that we're working with, in order to operate on them and to detect them and to manipulate them and to transmit them, we don't have the luxury of doing things that you can do with classical types of signals. So we can't just dump more power into our systems, or we can't just amplify those signals because that adds too much noise into the system. So we tend to have to think about efficiency at the very beginning and think about system-wide efficiency for these kinds of technologies. So I'm going to highlight a little bit of the work going on in my group and in this building, and then also at the end of the talk a little bit about some of the other efforts going on campus. But I think maybe a good question that some of you might have is, so the title here is the second quantum revolution. A good question might be, what was the first quantum revolution? Right? So to understand that and to put this work that we're doing on campus into a little bit of better context, we really have to go back like 100 years, a little over 100 years. So the beginning of the 1900s, to understand the first quantum revolution, the theory of quantum mechanics originated from observations of light, atoms, and electrons that we couldn't really explain with the existing theories that we had at the time. So for example, I'm showing here different atomic transitions and their spectral lines, the energy level structure of atoms. We really needed to develop quantum theory to be able to understand these kinds of basic elements. And at the time, this was really fundamental research. It was curiosity driven, right? There weren't really any conceivable applications or technology use cases at that time. It was really curiosity driven. Okay, so 60 years of sort of research, basic research, a little bit of technology development, and that's really what then led to what is called the first quantum revolution. And you can think of this as really, it's not, there's not much quantum about it. It's really classical technologies that came out of it, things like the transistor, the laser, atomic clocks. These technologies are largely classical, but they do require quantum mechanics to understand and predict their performance. And that's what we think of when we think about the first quantum revolution. And so, of course, these have led to really transformative technologies that have changed society, right? So thinking about the transistor, we all know the impact of that in terms of computing, right? And with the laser, we've heard a lot about that already in terms of displays, also like global networks, data centers, fusion energy, scientific discoveries like LIGO. These all leverage laser technologies. With atomic clocks, this allows us to have really precise GPS and navigation, for example. Okay, but we're now experiencing what's called the second quantum revolution. And so the so-called quantum 2.0 technologies, they really leverage the full power of quantum mechanics. And so this means things like superposition or controlling individual quantum objects very precisely, or things like entanglement and using these concepts of quantum mechanics for transformative applications and discoveries. And so entanglement, for example, is the ability to take two quantum objects and measure the property of one of these objects. And even if it's on the other side of the universe, by doing that measurement, that impacts the state of this other object instantaneously. So this is what Einstein called spooky action at a distance. And this idea of entanglement is really what we're trying to leverage for applications in quantum computing, new types of simulations of new materials, quantum chemistry, sensing like in LIGO or searches of dark matter, and also quantum secure communications. So to give this a little bit more of a context in terms of the roadmap of quantum computing, for example, and where we're at. So this is a nice chart that really shows the scale of the number of qubits or quantum bits in a quantum computer and in the timeline of that. Right? So on this axis is a log scale of the number of physical qubits in a system. Here's the timeline. Started sort of, in 1998 or so when we had, sort of individual qubits and it started ramping up. We're kind of right here in this regime right now where we have sort of tens to hundreds of qubits and maybe even some platforms that have like 1,000 qubits. And so a good question would be, well, is this enough? What can we do with 1,000 qubits? How many qubits do we need to actually make something like a useful quantum computer? So I want to highlight one example here that was in 2019, a demonstration by Google locally here in Goleta. And so the picture on the left here is a very nice image from one of their systems. You can see this device here. This is the actual quantum hardware itself. Everything else, these are just microwave lines. The rest of it is a refrigerator to cool down the whole system. This is really where that technology is. And so you can see there's a lot of systems engineering that has to go into actually making this thing useful. It's not just making some small little widget. You have to think about the whole system itself. So what they demonstrated was they took their device, their hardware, they compiled some random circuit operations on the hardware, and they compared that to what you might be able to get with some classical system like IBM's Summit supercomputer. So it's not a useful task. They didn't really do anything useful. It's more benchmarking of their hardware. And so with 53 qubits, they could demonstrate that it's a little bit controversial in terms of how much of an advantage they might have gotten from their hardware, but they at least demonstrated that there's some level of speed up on the computation for that specific task compared to a supercomputer. But what I want to really actually point out is, irrespective of whether there's a quantum advantage or not, I think there's an energy advantage. Right? So if you think about the amount of power required to run this system, and this is just sort of my estimates here, they might be a little bit off, but it's sort of tens of kilowatts of power to run their quantum system. If you think about the supercomputer, it's probably more than tens of megawatts, right? So you have a lot of power efficiency, and then depending on how long it takes to run that the hardware, you get even more orders of magnitude in terms of energy efficiency overall. So just thinking about quantum hardware overall, you're going to get a lot in terms of efficiency. Okay, so going back to this chart. So, that's kind of where we were at in 2019, where we had sort of tens of qubits. They could run sort of some of these contrived tasks that maybe weren't super useful, but a good benchmark for where the performance was. Where do we want to get? We really want to get up to this point here in this plot where we have like 1 million qubits. And the reason we need something like 1 million is that these qubits tend to be noisy. There's errors. Correcting for those errors is hard. We need to build in a lot of redundancy into these kinds of systems to actually make them useful. So estimates are, on the order of 1 million. And if you look here, so this point here is by a company in Palo Alto, PsiQuantum, who's working on optical technologies. This is their prediction that they'll have systems with 1 million qubits in 2026. It remains to be seen, so we'll see in a few years if that's really where they end up and if we have to update this timeline or not. But looking at their system, people maybe picture quantum computers as being sort of this widget or this box, something like the size of a computer. It's not going to be that. It's going to be a giant warehouse, much like a data center, where you have these different racks of different modules and different hardware that have very specialized functions, and it's going to be this huge, massive system. That's the only way to get up to that level of like 1 million qubits, just in terms of space and how much it takes. And so in PsiQuantum's approach, for example, it's an all-optical approach. And one of the main reasons one may want to use optics is the fact that most of the hardware works at room temperature, so you don't have to cool it down. So you don't need all of these refrigeration systems. Now, some of the specialized hardware they use does require to be cooled down to cryo temperatures, but at least most of the system can operate at room temperature. And then if you think about a quantum computer being these server racks in a giant warehouse, and you need to send signals between them. And these are quantum signals, right? So we need to preserve the quantum state of these signals. You're going to send those over fiber optics, right? So if you're making your quantum computer based on an optical system, then it's much easier to then take those photons out and send them over fiber optics because you're already working with photons in the first place. And one of the key resources for this is the fact that it's powered by entanglement, right? So you need to generate entangled photons, these photon pairs that have these strong correlations between them, and then you need to distribute those photons across fiber networks. Okay, so last year's Nobel Prize was about entanglement and generating entangled photons and doing measurement on those photons. And if you actually look at the experiment, this is one of the first experiments. This was in like the 1960s and 1970s. It was sort of a lab scale experiment. So this is John Clauser. He was working in the basement of Berkeley, and they were using, I think, cesium atoms to basically pump them with the laser and generate entangled photons that way. You have a detector right here. This is a photomultiplier tube. You have another detector back here. I think they have like a jet of atoms kind of flowing through this system, and they just start pumping the atoms and generating the photons. So this is a lab scale experiment to be able to try to prove that they had entanglement with the photons that they were generating. A pretty cool picture. And you can see here's sort of the electronics rack behind them. These are all analog electronics to do all of the timing, synchronization, detection, and everything. Okay, so 50, 60 years pass. There's been lots of advances in laser technology, detector technology, and electronics, and we can build the exact same sort of apparatus that is maybe just a couple feet, by a couple feet. So it doesn't take an entire lab. And it's stable and simple enough to use that we're using it for one of my classes to teach undergrad students how to run these systems, how to generate entangled pairs, how to do those kinds of measurements. So if you're interested in any of this, I'm going to help lead some of the lab tours after this on the first floor. We can swing by and take a look at these modules if you're interested to see how we can do it, at least for the educational labs. Okay, but we can do even better. So we can use integrated photonics to further scale and make more compact and more efficient devices. And that's a lot of what my research actually focuses on. So here at UCSB, we have a long history of really good materials science, materials development, and integrated photonics. So we have the 3.5 materials growth facilities, the nanofab facilities here, and in Henley Hall where my lab is. I'm fortunate enough to be in here with state-of-the-art optics lab space. We can perform all the experiments and testing of the devices that we're making. So you can take these sort of lab scale experiments and put them down onto sort of a optical setup that looks like this and use that for educational purposes. Now we can put those kinds of experiments onto an integrated photonic chip this big, right? And so that's what this is showing here. You zoom in on here, and here's the same sort of thing. So this kind of photonic device is producing entangled photon pairs, and it's probably more than 1,000 times more efficient than these bulk tabletop systems. So we're dramatically reducing the amount of power that's required to actually generate all of these photon pairs from these kinds of devices. And we can do even better than that. So using integrated photonics, we can start thinking about scaling and putting more and more of these sources into a single integrated photonic chip. So this kind of device here, which is 1 square millimeter, there's one source on here. We can just pack in a bunch more. So this is a device where we're multiplexing lots of these sources onto one device, so we can get a further improvement of 10 to 20 times in terms of the efficiency of these kinds of devices. So as a proof of principle, a recent experiment that we were working on that's now posted on the archive and under review is distributing entanglement across the UCSB campus. And so we found access to the fiber server in this building, and we're able to then connect our pair source to that server, send photons through the fiber optic that's going underneath Mesa Road. It actually goes to the campus police station. And we basically, so it's very secure on that end. And so then we send the fibers back, the photons back over a different fiber back to our lab in Henley Hall, and we can distribute entanglement and test how, any sort of perturbations to the fiber, cars going over the road, temperature fluctuations, how that's impacting how we can distribute the entangled photon pairs. And so the students in my group have done that and demonstrated that we can encrypt information in this sort of capacity using entanglement. So you can take something like the UCSB logo, for example, encrypt it and then decrypt it using this fiber-based system. And that's all very stable. And these are not specialized fibers. These are just fibers that were already laid at some point that they were going to use for connecting the two buildings. And we just said we're going to take over that fiber for a little while at least. Okay, so maybe some other near-term applications that we're working on in collaboration with John Bowers and also a local company, Nexus Photonics, which Min is here helping to lead this project, is taking chip-scale lasers. So Steve has talked a little bit about this. We work at slightly different wavelengths for our applications. This is like 780 nanometers or 1550 nanometers. Taking chip-scale lasers, taking our chip-scale quantum light sources, combining them and packaging them up. And because they're compact, because they're efficient, you can imagine putting these things on satellites. Right? So you can use this for space-based entanglement distribution, space-based quantum networks, and secure quantum communications. So we have collaborations with Nexus and with John Bowers UCSB and a couple of programs with NASA and Air Force to do this. Okay, so maybe looking forward a little bit for the next 5 or 10 years and where are we going to go. So just to remind you with this chart, here's kind of where we're at right now with maybe like, 1,000 qubits that are sort of noisy, so we can't do anything super useful with them yet. And we really want to go higher. We want to get up to here where we have maybe 1 million qubits or less noisy qubits. And I would say maybe the $1 trillion question is, how do you do that? And I don't have a great answer for that. I don't think anyone necessarily does have a great answer for that yet, but there's a lot of research into this area to figure out that answer. How far can we push that? So maybe I'll make a couple of predictions and maybe give a couple of years here in terms of what I think we might see. So I think within 5 years, we're going to see space-based quantum networks with satellite to satellite, satellite to ground entanglement distribution. Around the world, there's different agencies that are already putting up satellites with entangled photon pair sources on there. And now it's a matter of getting these satellites to communicate with each other. So it's low loss. You can send signals in space, and then you can have sort of beam lines for uplink and downlink coming down to observatories. I think we're going to see that within 5 years. We're already seeing some of that infrastructure being laid right now. Another interesting area is in quantum sensing, and I think this is going to be an impactful area, is basically using quantum mechanics to make more sensitive devices like magnetometry or for navigation or biotype sensors. And so we're already seeing some impact in that area now. And then for quantum computing, I think if you ask me, how long is it going to take us to have a useful quantum computer, I may give you one answer one day and a different answer the other day. I would say we might have useful quantum computing hardware maybe within like 10 years. I don't think it's going to be a universal quantum computer that everyone envisions where it can solve all the world's problems. That's going to take much longer. But I think we're going to start to see more useful quantum computing applications emerge within 10 years. I don't think we necessarily need to hit the 1 million qubit benchmark to be able to do that. Okay, so maybe to conclude, I just want to highlight some other research going on campus and in the institute and in the building. So we have the Quantum Foundry on campus that's been around for a few years, a little bit before I got here. $25 million center to fund quantum materials and sort of entangled devices research with directors Anya J.H. and Stephen Wilson. Recently, David Weld led an effort through the NSF for training, and so some of the work that I'm working on the quantum photonics lab to train students is also a part of this in terms of graduate student training in the hardware. And then recently, there was a call out for developing quantum sensors and useful quantum sensors. So not just quantum sensors that are stuck in our lab where maybe we can do some useful research, but actually getting them out of the lab and into the hands of users who want to use the sensors. So I think there were 18 teams funded, and 4 of those teams are based here at UCSB. So I'm leading one of those teams. Andrew J.H. in physics is leading another team, and then Dan Blumenthal and Anya J.H. are also part of other teams. Okay, so I also wanted to highlight there's a lot of students that are actually doing all of this work. They're the ones that are actually working on these projects. Some of them will be helping with some of the lab tours, so you may see them around on the first floor, and then lots of collaborators, including John Bowers. So with that, I'll conclude, and thank you all, and happy to answer any questions.
All right, let's take our speaker. All right, thanks, Galan. Wow, more cool stuff. So questions for Galan? Yeah.
Hi, thank you so much for your talk. I'm doing computer science and computer architecture research, so it's related to software hardware. I see a lot of people doing like quantum architecture right now, and my understanding is there's a very serious constraint on the temperature to operate qubit. Right, this qubit can only work in 0 Kelvin.
I'll stop you right there. That's not necessarily true. So it depends on the system that you're working with. So with the photonic qubits that we develop in my lab, those survive at room temperature. That's the nice thing about the photons. They're very insensitive to everything going around their environment. The one thing they're sensitive to is loss. So if we lose the photon, we have a problem. And so that's where efficiency comes into play, where we want to make our system as efficient as possible so we don't lose the photon, but it's all at room temperature.
It's all room temperature. Okay,
Yeah.
so for superconducting,
That's got to be cryo. Yeah. Yep.
Close to 0 Kelvin.
That's right.
So what's the main bottleneck that is like making you say that the quantum computing hardware is like very slow, or something that we can see in 10 years, see a universal quantum computer? What is something that's limiting the direction that we can now see massive production industry or like universal use academia?
Yeah, that's a good question. So I think that timeline, the bottleneck in terms of how quickly can we ramp up is, it's not just the number of qubits. I think if Google wanted to, they could make 1 million qubits. That's fine. They've probably already made millions of qubits. It's a matter of how good are the qubits. So the noise, the performance, when you operate on these kinds of bits to try to flip them between 0 and 1, how noisy is that? How good have you actually operated on those qubits? And then as you try to scale up, that tends to make them a little bit noisier. And so you get more errors. And so it's a matter of optimizing the full system where you can scale, but you aren't also increasing the errors in the system. Yeah. Yep, thanks.
Okay, thanks. Back in the corner, a question.
Maybe chicken or egg, AI and quantum, which comes first? Does AI help quantum, or does quantum make AI?
That's a good question. You don't need quantum for AI. I think AI may be able to help quantum. Yeah. I think you're going to see impact on AI much sooner than you will with like quantum computing, for example. You're already seeing that impact.
Nice question. I like it.
Yeah, it's a good question.
All right. And any final question? Okay. Galen, thank you
Thanks,
very
everyone.
much.